Welcome to Electrical Lad, your trusted source for simplifying electrical, hydraulic, and pneumatic concepts in a clear and practical way. If you're new to the channel, be sure to hit the subscribe button and turn on notifications so you never miss an upcoming video. Looking at a hydraulic schematic for the first time can feel like trying to read a treasure map or solving a puzzle. It seems confusing at first, but it's actually quite logical once you understand the symbols. But don't worry. In this video, we'll break it down and make it simple. By the end, you'll understand the symbols for the main components: actuators, pumps, control valves, and accessories. Knowing these is crucial because they form the backbone of any hydraulic system, helping you troubleshoot, design, or simply understand how things work. Let's jump in. Let's start with the hydraulic reservoir, or tank. Think of it as the storage for hydraulic fluid. It's where the system gets its steady supply of fluid to keep everything running smoothly. Next, hydraulic pumps are the heart of a hydraulic system, driving the flow of fluid that powers all the components. They convert mechanical energy into fluid power, ensuring the system runs smoothly. When you see an M inside a circle on a diagram, it represents an electric motor that operates the pump. Next in the system is the check valve, a critical component that ensures fluid flows in only one direction. Although some designs omit a check valve after the pump, I always include one to prevent back pressure on the pump. This simple addition enhances the pump's performance and boosts the system's overall efficiency. Now let's look at the relief valve. In a hydraulic system, a relief valve controls pressure by releasing excess fluid as needed. It opens to allow fluid to return to the tank and keeps the system pressure at a preset value. In this example, we have set the relief valve to 1000 psi, or 69 bar. Sometimes the system is equipped with an additional relief valve, referred to as the secondary relief valve. This valve serves as a safety backup, providing protection in the event of a primary relief valve failure. Typically, the safety relief valve is set 20% to 30% higher than the main relief valve's pressure setting. Next up is the hydraulic actuator, or cylinder. It takes fluid power and turns it into linear motion. But how many types of actuators are there? There are 4 main types of hydraulic actuators, each designed for specific tasks. 1. Single-acting hydraulic actuator. This type moves in one direction using hydraulic pressure, and then a spring or gravity brings it back to its starting position. 2. Double-ended actuator. It has a piston rod on both sides, which allows it to move with the same force in both directions. 3. Telescopic actuator. These are made up of several stages that extend outward, like the sections of a telescope, providing a long reach while saving space. 4. Double-acting hydraulic actuator. This one uses hydraulic pressure on both sides of the piston, so it can move back and forth without needing any external force. This is the type of the actuator we are using in our example. Now let's dive into directional valves, a topic that can seem a bit complex at first, but don't worry, we'll break it down step by step to make it easy to understand. Before we cover directional valves, do me a quick favor. Hit that like button, subscribe, and tap the bell icon. So how does a hydraulic directional valve actually work? A hydraulic directional valve is made up of 3 main components: the body, the ports, and the spool. First, the valve body is the main structure that houses all the internal components. It's designed with precision to allow the spool to move and fluid to flow through the correct ports. In this example, I'm using a 2-way directional valve. It's called a 2-way valve because it has 2 ports, port P and port A. When the spool moves to the left, what we refer to as a spool shift, the oil flows from port P to port A. But how does the spool actually shift? There are several common methods to accomplish this, including levers, foot pedals, solenoids, pilot-operated systems, and solenoid-controlled pilot-operated. Each method has its place in the industry, chosen based on the size of the valve and the system's requirements. Now let's go back and focus on the directional valve in our hydraulic system. This is called a 4-way valve because it has 4 ports. P is for pressure, where the fluid enters. T is the tank port, where the fluid returns to the reservoir. A and B are the working ports that connect to the actuator to control its movement. The valve is also known as a center-blocked valve because, when the spool is in the center position, it blocks all 4 ports. Additionally, This is a solenoid-operated valve because the spool shifts to positions A or B when a solenoid is energized. The valve uses springs to return the spool to its neutral center position. Now that we've covered the basics, let's break it down. This is a four-way, three-position, solenoid-operated center-blocked valve. Let's see how it works. When the valve is in the neutral position and no solenoids are energized, the spool is centered, and the ports are blocked. When solenoid A is energized, the spool shifts to the left, directing pressure from port P to port A and connecting the tank port T to port B. This action causes the cylinder to extend. In the next clip, pay close attention to the valve operation to see how this process works. An important practice is to de-energize the solenoid A once the cylinder is fully extended. This ensures the cylinder stays extended until solenoid B is activated. Note that this applies only to valves with center-blocked positions. Now let's talk about retracting the cylinder by energizing solenoid B. Let's start again with the cylinder fully extended and the directional valve in its center position. When solenoid B is energized, the spool shifts to the right, connecting pressure port P to port B and port A to the tank. This causes the cylinder to retract. In the next clip, pay close attention to the valve operation to see how this process works. Next, let's talk about flow control valves. These valves are used to adjust the flow of fluid, which in turn changes the speed of the actuator. In our system, we're using a directional flow control valve. This means it only controls the flow in one direction. There's a check valve on the outlet side that makes sure the flow goes through an adjustable opening or orifice. A good rule of thumb is to use the flow control to regulate the flow as it exits, which is called meter out. This method generally provides smoother operation than controlling the flow when it enters. Now that we've gone over all the key details about our circuit, it's time to discuss the different styles of valves. Understanding valve variations is essential when working with hydraulic schematics and design applications. Let's break it down step by step to make it clear and easy to follow. But before we dive in, if you haven't subscribed to the channel yet, please take a moment to do so. It really helps us continue creating valuable content for you. First on the list is the tandem center valve. In its neutral position, the pump port connects to the tank port, allowing fluid to flow freely back to the reservoir. At the same time, the work ports A and B are blocked, preventing any movement in the actuator. This setup helps save energy by letting the fluid return to the tank without forcing it to pass through the relief valve at the system set pressure. The downside of a tandem center valve is that the pump can only supply the circuit with the tandem center. It can't be used for other circuits because when the valve is in the center position, the pump pressure drops to nearly 0 psi. This means the pump isn't building pressure to operate anything else while the valve is centered. Next is the open center hydraulic valve, also known as an H-center valve. When the valve is in the neutral position, the work ports are open to the tank, meaning the actuator isn't locked or held steady. It's free to move if there's an external force acting on it. At the same time, fluid flows freely from the pump back to the tank, which reduces pressure to nearly zero. Like the tandem center, this setup is great for reducing strain on the pump, but it's limited to a single circuit. Next, let's talk about the float center hydraulic valve. In its neutral position, the work ports connect directly to the tank, allowing the actuator to move freely under load without resistance. Unlike tandem or open center valves, the float center valve doesn't route pump fluid back to the tank when centered. This design allows the pump to operate multiple circuits, as the fluid flow isn't diverted. There's one more commonly used valve worth mentioning, which doesn't have a center position: the four-way solenoid-operated spring return valve. In operation, when the solenoid is energized, the actuator will either extend or retract depending on how the valve is configured within the circuit. Once the power is turned off, the spring mechanism takes over, causing the actuator to reverse direction and return to its original position. Now that we've covered the basics of a simple hydraulic system, let's dive into some questions about more advanced systems. What exactly are hydraulic accumulators, and why are they so important? How do we handle overhung loads, and what role do counterbalance valves play in this? And how can hydraulic systems filter and cool the oil automatically without manual intervention? Let's explore these one by one. Think of hydraulic accumulators as backup batteries for hydraulic systems. They store pressurized fluid and release it when needed. There are several types of hydraulic accumulators, but the two most common are piston and bladder types. Piston accumulators have a piston that separates the gas and hydraulic fluid. They are durable and handle high pressures, making them ideal for heavy-duty applications. Bladder accumulators use a flexible bladder to separate the gas and fluid. They respond quickly to pressure changes and are widely used in mobile and industrial systems. So, what exactly are accumulators used for? The first major use of an accumulator is to maintain system pressure. It's especially helpful when the pump isn't quite large enough, or when there's a sudden demand for high volume that could cause a drop in pressure. The second use of an accumulator is to absorb shocks. When valves shift quickly, it can cause vibrations in the system, leading to damage or leaks. An accumulator helps cushion these shocks. The third use of an accumulator is as an emergency backup. If the pump fails, the accumulator's stored energy can be manually used to move the actuator into a safe or neutral position, keeping the system secure during emergencies. In our example, if the pump fails, the check valve allows the accumulator to keep the line pressurized. This stored energy can then be used to move the actuator, either by manually operating the override on the four-way directional valve or by energizing the valve's coil. Accumulators are incredibly useful in hydraulic systems, but they can also be dangerous if not designed properly. Why? Because they store fluid energy. When the system is shut down and in a zero-energy state, there must be a way to safely drain the accumulator back into the tank. If not, there's a risk that someone might accidentally energize a valve, causing unintended actuator movement, potentially leading to serious injury. In this circuit, we have a solenoid-operated normally open two-way valve that connects the accumulator to the tank. This setup ensures the accumulator can only be pressurized when the valve is energized, as energizing the valve blocks the drain port. A manual two-way valve can also be used to drain the accumulator into the tank when the system is shut down for maintenance. Let's talk about overhung loads. Unlike horizontal loads, you can't use the same circuit design for overhung loads because gravity plays a major role here. Imagine a 5,000 pounds load hanging from a cylinder in this example. When the directional valve is energized to lower the load, it free falls, much like dropping a heavy stone from the top of a mountain. This happens because the rod end of the cylinder's port shifts to the tank with no resistance to counteract the gravitational force. You might wonder, why not use a flow control to slow the free fall? The problem is, if you reduce the flow too much, it builds up high pressure at the rod end of the cylinder, which can damage the packing. To exaggerate this, imagine the flow control is fully closed. The pressure could skyrocket to 1,000 psi, plus the full weight of the load bearing down. With nowhere for the oil to go, all that force piles up on the packing like a pressure cooker ready to explode, eventually causing it to fail. So, how do we solve this problem? The solution is coming up next. The answer is a counterbalance valve. It's a normally closed pressure control valve designed to balance or counteract a load. The pressure is usually set to create a force equal to or slightly greater than the overhung weight. This pressure is calculated based on the rod end piston area and the weight of the load. If you have any questions about counterbalance valves or how to calculate the pressure settings, feel free to drop me a note in the comments. With overhung loads, we usually add a pilot-operated or solenoid-operated check valve along with the counterbalance valve for extra safety. This helps keep the load securely locked in place. In our example, when the directional valve is energized for downward movement, the pilot senses pressure at the blind end of the cylinder and opens the check valve. This setup is commonly used in presses. And just a quick tip, pilot lines are always shown as dashed lines in diagrams. Just like the oil in your car engine, the oil in a hydraulic system heats up and gets dirty over time. That's why we need a way to cool and filter the oil to keep things running smoothly. There are 3 ways to filter hydraulic oil. The first is by using a properly sized pressure filter on the pressure side of the system. Honestly, this is my least favorite method. As the filter gets clogged, you'll see a pressure drop across it, which reduces the oil flow. Plus, it requires extra attention to replace the filter on time to avoid issues. The second way is to use a return filter. With this method, the oil gets filtered as it flows back into the tank. Since the return line pressure is almost zero, you don't need an expensive high-pressure filter. This makes it the most cost-effective way to filter the oil. The third method is called kidney loop filtration, and it's also the most expensive option. This setup uses a separate pump and filter, which continuously cycles oil back to the tank. Since the pump operates at very low pressure, almost zero, you can use a return filter here as well. This method is typically used for large hydraulic systems with multiple actuators and valves. Now let's talk about cooling hydraulic oil. This is done using a heat exchanger, which can be either air-cooled or water-cooled. An air-cooled heat exchanger works like the radiator in your car. Oil flows through tubes, while air passes over the fins to cool it down. For a water-cooled heat exchanger, the oil flows through tubes, and water circulates around them in the shell to absorb the heat and cool the oil. Regardless of the type of heat exchanger you use, they're only designed for low-pressure applications. They can't handle high pressure. There are two methods available. The first method is to install the heat exchanger on the return line after the filter. This way, the oil flows through the filter first, then through the heat exchanger, and finally back to the tank. The second method is to install the heat exchanger in the kidney loop filtration system, right after the filter. In this setup, the kidney loop pump continuously circulates oil through the filter and then through the heat exchanger. This approach is usually used in large hydraulic systems with multiple actuators and valves. Great job sticking with it. Hydraulic schematics might seem overwhelming at first, but now you've got a solid understanding of the main symbols for actuators, pumps, control valves, and accessories. These are the building blocks of any hydraulic system, and knowing them will make troubleshooting and designing so much easier. If you enjoyed this video, give it a thumbs up, hit subscribe, and feel free to leave any questions or thoughts in the comments below. If you're interested in diving deeper, I've included some suggested readings in the description. Thanks for watching Electrical Lad, and I'll see you in the next video.